Okay, okay. Now energy losses in hydraulic system. So when we have an hydraulic system, we are pumping the water or fluid into the system. As soon as this fluid moves towards the from point A to point B, over a period of time, the work has been done. So there are some losses, energy losses, in the form of the noise, in the form of the friction, in the form of the heating, and so on. So the fluid closer to the pump has different energy as compared to at the outlet. So we have different energy. Some of that energy is lost between the length of the pipe, between the length at from point A to point B. We want to minimize these energy losses. The higher the energy losses, the more powerful pump you have to use. The more powerful pump you have to use, it means you are paying extra, consuming extra energy, so they're not energy efficient. um, so first thing, we will have a look at the laminar and turbulent flow. What is a laminar flow and what's the turbulent flow? We will also look at the Reynolds number, and we will see why this number is important in reference to laminar and turbulent flow. We will have a look at the Darcy-Weisbach equation, and we will see where we use that equation in terms of hydraulics. Okay. Now, depends on the viscosity of the fluid. Every fluid has different viscosity. Because the viscosity of the fluid is different, viscosity is defined as resistance to flow. If something has a high viscosity, it has more resistance to flow. Honey has high viscosity as compared to engine oil, which has low viscosity. Viscosity of the fluid relates also a function of temperature. Higher the temperature, the lower the viscosity is. Lower the temperature, higher the viscosity is. Now, if we want if we are looking at energy dissipation into the system, and let's say we got a pump, and the pump is pumping the high viscous solution from point A to point B, the pump has to work extra hard, because as the fluid moves to inside the pipe, it causes friction with the surface of the pipe. Because it causes a friction with the surface of the pipe, it will generate extra heat. Going back to the first law of thermodynamics, energy cannot be created, it cannot be destroyed. So that heat energy, the pipe which is heating the pipe because of the friction or high viscosity fluid being pumped from point A to point B, that energy is the lost energy which we can avoid. Now, where does energy losses occur? Energy losses occurs in valves, fittings. Now, there are various types of fittings. Bends, there are couplings, there are elbows, different types. Now, if every time the fluid actually moves in a straight path and then is diverting at an angle, it's causing a turbulence flow. It's causing there's something going on with the laminar layer of the flow. So we try to avoid that one. We try to have the pipe as long as possible, but sometimes we have to bend it. Okay, so we have to use some fittings. If we are using smaller size of pipe, the greater the loss of energy is. It's assumed there is a corridor, it's wide, and let's say or let's say it's wide and 100 people are passing in both directions. The people coming from the opposite direction, imagine these are friction, and this is where you are actually going from left to right and right to left, and they are causing friction. Now, Imagine if I reduce the size of the corridor, the thickness, the width, and now the same amount of people coming from both ends. But obviously there is not enough space, so there will be more friction, there will be more heat, hence the more energy loss. And this is what we try to avoid. This is why, like for example, in your house, you got boiler. Let's imagine in a building, they got a boiler, and I use a wrong fitting. I use a thin diameter copper pipe. What will actually happen when I turn on my boiler and I haven't done the suitable heating, ventilation, and cooling diagrams? I haven't applied that one. As soon as I turn on my boiler, after a while, that my um, pipes, I will hear some sound coming off my pipe, like squeaky sound, flow of water, and so on. These are all the losses. The more these sounds are, the more the pump will have to work, the more there will be reduction in pressure at the high altitude. So in buildings, they have to look into all these details, and they have to put like pump after a certain level to maintain the proper pressure. Okay. In many fluid power application, energy losses due to the flow in the valves and the fittings, they exceed the energy losses in the pipe itself. I'll imagine I'm using like so let's say 700 meters of pipe. In 100 meters of pipe, I have like 50 fittings, because fittings is diverting the flow of water and so on. And these 50 fittings are, let's say, 1 centimeter each, for example. So 50 centimeter. If I don't put these fitting in a proper place, the energy losses in these fittings, which are 50 centimeter in length, will be more than the energy losses in the pipe, which is 100 meters long. So we have to make sure we put in the proper place. Then we got a definition of a laminar and turbulent flow. Now, when the fluid actually flow in boundary layers, so which we cannot see. There is a boundary of the fluid, there is a one layer of fluid, then another layer of fluid, then another layer of fluid, and so on. And these layers of the fluid, they actually just move on top of each other, and we see that as one fluid. Now, because of these laminars, we call these layers as laminar. Imagine in this diagram, the fluid is flowing from A towards B, this direction, in the direction of the arrow. Now, and they are different layers. If the fluid is flowing, they will create the laminar. Now, the velocity of the fluid, which is u, is a lot higher in the middle as compared to the velocity closer to these ones, to the surface. The A diagram, this diagram, the first one, is an ideal fluid. That fluid does not exist in real world scenario. This is a real fluid. Yep. This is how the fluid behave in real life. So the friction at the surface of the pipe, because it's at the pipe, is a lot more as compared to the friction in the middle. So the fluid in the middle will have less resistance, and it's going to flow faster as compared to the fluid at the surface. Now, this is a proper laminar flow because we can see the layers and the layers and the layer. Not always is that the case, because sometimes there is turbulence. So how do we define the laminar flow and a turbulent flow? Now, when we look at the laminar flow is a streamlined fluid that is flowing in one direction. The fluid is consist of a very like infinite small layers, and these layers are at very tiny thickness, and they are gliding on each other. If they are gliding and their direction does not change and they move in the same direction, it's highly likely it's going to be a laminar flow, non-turbulent flow. Okay. Now, if the particle, imagine um, this is the surface. Yeah, this is the velocity profile. Velocity profile is how this thing is actually moving. Yeah, and the fluid is moving in this direction. Now, this will be a classical case of a laminar flow. Now, laminar flow, there is a definition. It has the particles. Yeah, they move in a streamlined fashion. So they all move in a streamlined fashion. But when we look at the turbulent flow is a flow where the boundaries of a liquid, they move in a random direction. The movement of the particles, they fluctuate. They can move in any direction. They can move in direction perpendicular to the direction of the flow of liquid. So it's here. Maybe imagine this is a bend, and as soon as it enters the bend, it actually moves. So they actually move in that way. But as soon as they actually did a 90-degree turn, it caused a pushback, turbulency, and that was going to interact with the laminar or the layers coming from this way. And this is where you will see noise and so on. This is where you will see energy losses. With the elbow joints and all these joints, there is a good thing about that as well, because when you put these joints, this at the joints, a lot of turbulence is happening. This is where a material degradation, corrosion, yeah, rusting, all thing is going to happen. So rather changing the whole pipe, we can only change that elbow joint and put a new one. Now, when the fluid is coming horizontally and straight away it takes a turn, what actually happened? It generates the turbulence with the colliding particle from the 90-degree angle bend. And it caused more resistance. Not only it caused resistance, it caused the energy losses, and the laminar flow is disturbed. In a turbulent flow, there is an irregularity. There is no definite frequency, as in wave motion, like it's not a proper flow. There is no pattern, and there are large kind of eddy currents or eddies losses. Eddy losses are the losses that are in opposite direction of the initial direction of the flow of liquid. Now, this is a typical example of a turbulent flow. So you can see these laminars, they're not flowing in laminar, they are in haphazard different directions, and hence they will cause energy losses, because every particle that moves from left to right carries the kinetic energy, carries the potential energy, and carries the internal energy. But as soon as it actually moves in a random direction, the other particle, other layer, when it comes and collide, it will lose its energy, and energy at the outlet will be a lot lower than the energy at the inlet. Now we got the Reynolds number. Now we assume when we talk about fluid, we talk about anything that's not solid. So liquid and gases, they both are classified as a fluid. Okay, there is a term called capillarity. Capillarity is if you got a glass of water, and you just have a tissue roll, you just like make the tissue roll like in that kind of shape and put that in a glass of water. You can see the level of the water rising up. There are many phenomena. One of the phenomena there is capillarity. Capillarities is there are tiny, teeny, very tiny veins, kind of veins inside the tissue paper. So what actually happens is they pull the water. They pull the water. Yes. Okay. Now, if you rather having a water, if you put an oil, petrol, let's imagine, which has less viscosity,